A typical example of an open system is that of a surface which is in contact with the surrounding gas. Initial experiments have been performed by Irving Langmuir in the beginning of the 20th century, where he looked for the absorption of water molecules on surfaces at different water vapor pressures and at different temperatures. Now what he found is that depending on the vapor pressure, the amount of gas is changing. He also found that this is not a linear process. At a given pressure, the amount of water molecules on the surface did not increase. Further, he found that this saturation behavior was strongly dependent on temperature. We will use the description of the grand canonical ensemble in order to understand this behavior. We consider the surface as an assembly of n 2D lattice sites. Each of the sites can be occupied by a single particle. The occupation of a site lowers the total energy of the system by epsilon. Further, the surface gas is in equilibrium with the gas around, held at temperature T and at pressure P. For this model, the grand canonical partition function reads lambda as a function of alpha, beta, and n. Remind you, n is the number of lattice sites, which in this particular example replaces the volume of the system. Now, this is given by the sum on all n equals to 0 to capital N, meaning from zero occupation to full occupation, e to the minus alpha n times e to the minus beta n times epsilon times the binomial coefficient n choose n, which describes if I have small n particles that are distributed into capital N sites. Now we can rewrite the equation in order to look like the binomial sum that is solved to lambda is equal to 1 plus e to the power minus alpha minus beta epsilon to the power n. Now, in order to understand the experimental results from Langmuir, what we are interested in is the mean occupation. The mean occupation F is defined as the mean number of particles occupying the n possible positions. Now, from the partition function, we derive this expression as minus 1 divided by n del log of lambda by del alpha. Solving for that, we obtain this is equal to e to the minus alpha minus beta epsilon divided by 1 plus e to the minus alpha minus beta epsilon. Now what we are interested in is how this mean occupation depends on the parameters of the external gas. The surface is clearly in equilibrium with the surrounding gas, which means that the affinity of the surface must be equal to the affinity of the ideal gas at given temperature and pressure. Now the affinity of the ideal gas we derived in an earlier clip, reading ln lambda thermal to the power 3 times beta p. Now filling this result into the equation for the mean occupation now gets a form that F is equal to P divided by P plus P0, where P0 is e to the power beta epsilon divided by beta lambda thermal to the power 3. Our result clearly confers the experimental results of Langmuir. For very high pressures, P0 is irrelevant and the occupation goes to 1. For very small pressures, the occupation linearly scales with the external pressure with a temperature-dependent increase of a slope which is proportional to t to the power minus 5/2. Now this latter result is an important technological result. If you want to generate high vacuum, one of the problems is the water vapor that is absorbing to the surfaces. What this result tells us is that you have to heat up the chambers in order to get rid of this adsorbed water. This is why ultra-high vacuum chambers are typically covered by heat pads.